Good day, everybody. For those of you not familiar with prime signature, let's do a couple of examples here. The other set 2 is sometimes referred to as a multi-set, I think. And an example of an integer with a prime signature of 4, 2 would be, say, 5 to the 4th and 11 squared. And again, you can replace 5 and 11 with any primes you want. And I don't think they have to be distinct either. Now also, there's nothing special about the assignment of the exponents here. You could also write it as 11 squared. 11 to the 4th times 5 squared. And both of these numbers have the same prime signature. They're certainly different numbers, right? And of course, this would be the bigger number right here. Now, this sometimes is called a multi-set right here because you could have like 4, 2, 1, 1, 1, or 1, 3, 3, 2, 2, 6, 6, and you keep track of your, they're just exponents. They have to be positive integers, okay? Now today we're looking for the least positive integer k that would satisfy this equation that involves the number of divisors and the sum of the divisors and the number itself. So we're looking for the least value of k. And of course that would be just equivalent to finding the smallest value of this sum right here, okay? Now, it's very clear that this is the smallest signature 4-2 integer right here. Assigning the 4th power to 2, and then these are the two smallest primes, and then you want to keep the larger exponent with the smaller prime. That's crystal clear. Another possibility would be 3 to the 4th 2 squared, but that's a larger number, right? Okay. And everything else follows the number of also it's maybe not quite as clear, but the sum of the divisors are going to be less for this than for, say, 3 to the 4th 2 squared, okay, because you would have the same number of divisors, but they would be bigger divisors, okay? And that's another thing that's interesting about this. The d sub n is the same, okay, independent of the magnitude of the integers. The number of integers is going to be the same independent of the magnitude of the integers, okay? And so let's move along. Now let's see here. So we have this, which, let's see, where are we at here? Oh yeah, yes, okay. So we have this. We're just filling in the numbers here. D of n cubed is equal to this. And y'all, that's just because to find the number of divisors, you increment each of the exponents and then take a product. And that's because you have to allow for the exponent of zeros, because obviously you can have ones as divisors of the original number. Okay. Now down here, this is the sum of the divisors formula. And one way to see why that's true is just think of what this really is. The sum of the divisors of this integer right here, it would have to include 1 plus 2 plus 2 squared plus 2 cubed plus 2 to the 4th. And I think a lot of you probably recognize that this, I put it in parentheses, okay, and it's similarly over here, okay? You would have the same thing, except it would just go up. Well, I'll just write it down. 1 plus 3 plus 3 squared. This literally is the sum. That's the special thing about prime numbers. These are the only divisors. They're the only ones owing to just the uniqueness of the prime factorization. So you see, this product is going to generate other divisors of the entire number n, right? And you'll notice that this piece right here is just the sum of a finite geometric series with common ratio 2. Sum of a finite geometric series with common ratio 3. Okay, so that's why that works. And this is 31 times 13. And so everything's pretty routine here. Our original equation without the constant just becomes 15 cubed plus 31 times 13 right here. And then the number itself was 144, right? And so this all implies certainly that k must equal to 3922. It's the smallest such k. Hey folks, again, a fairly straightforward problem. It would have been trickier had the functions not increased together, but it's clear that all these functions are going to increase together. The sum of the divisors, the number itself, of course, and then this just stays constant. Okay, but the sum of the divisors is going to increase along with the size of the number in this context. And again, that's a little bit of hand waving right there, but I think it's very, very believable just because the number of divisors are going to be the same for the same prime signature, but if you swap around the bases, you're going to get larger divisors. There's no doubt about that. And let me just be a little more specific. Another possibility would have been 3 to the 4th times 2 squared, right? That would have been, this is supposed to be a 3, folks. 3 to the 4th times 2 squared. And it's clear this has the same number of divisors because you just ink the exponents to get the same thing, right? However, the divisors will be larger owing to the fact that you have 3 cubed and 3 to the 4th, which you didn't have over here. All right, so that's crystal clear. I don't think that requires a formal proof. All right, so I don't have any doubt that k equals 3922 is the solution. So let's write it over here. K equals to 3922. And again, I would call this not a difficult competition problem. Maybe junior level SMO. Okay, that's all. Thanks for viewing.